What if the worst thing that ever happened to an aircraft program turned out to be the best thing? What if being cut off from the world's most advanced technology overnight without warning didn't kill the program? What if it actually unlocked it? That sounds like wishful thinking, the kind of spin you put on a disaster to make it feel manageable. But by 2026, the MC-21 is proving something that nobody predicted, and honestly, something that even its strongest supporters weren't sure about. The engineers aren't just replacing foreign components. They're beating them, not in every area, not without struggle, but in ways that are documented, patented, and measurable. The aircraft emerging from this forced reinvention is outperforming the version that relied on foreign technology. This isn't a survival story anymore. This is something far more interesting. If deep technical aviation breakdowns are what you're here for, subscribe right now and hit the bell. What you're about to hear genuinely surprised me. Let's get into it. To understand what makes 2026 so significant for the MC-21, you need to go back to the beginning. And the beginning is uncomfortable. When the MC-21 was conceived, Russia made a calculated decision. Rather than developing every component domestically from scratch, a process that would take decades and cost enormous resources, the program would integrate the best available global technology: foreign composite materials, foreign structural components, foreign manufacturing inputs. On paper, it was a perfectly rational approach. It's what modern aerospace programs do. The 787, the A350, even China's Comac C919 used foreign systems extensively in its early configuration. Global supply chains exist precisely because no single country excels at everything. But here's the hidden risk that nobody talks about openly. When you build a critical national program on foreign supply chains, you're not just buying components. You're buying dependency. And dependency, in a world where geopolitics can shift overnight, is a vulnerability that no engineering team can design around until it's too late. For the MC-21, too late arrived faster than anyone anticipated. Sanctions hit. Supply lines closed. Critical materials and components that the program had been designed around, suddenly simply unavailable. And this is where the story gets genuinely fascinating. Because at that exact moment of maximum pressure, something unexpected happened in the engineering teams working on this aircraft. Instead of treating the forced redesign as damage control, instead of rushing to find the closest available substitute and moving on, engineers made a different choice. They decided to question everything. If we have to rebuild these systems anyway, why rebuild them the same way? Why accept the design assumptions baked into the foreign components? Why not go back to first principles and ask what the optimal solution actually looks like? That decision, made under pressure with limited resources and a ticking clock, is what's producing the results we're seeing in 2026. But what does that look like in practice? What does better than the original actually mean when we're talking about aircraft engineering? Let's start with something small, almost invisible, a gap in the wing. In April 2026, Russian engineers filed a patent for an improved flap design on the MC-21. Now, I know what you're thinking. Flap design, patents. Not exactly the stuff of gripping documentary. Stay with me, because this is where it gets genuinely clever. First, what are flaps and why do they matter so much? Flaps are the movable panels on the trailing edge of the wing. When extended during takeoff and landing, they change the wing's shape, increasing its surface area and curvature. That generates more lift at lower speeds, which is what allows a heavy aircraft to take off on a runway of finite length and land without approaching at dangerously high speed. Every commercial aircraft has them. They're not optional. They're fundamental. On the MC-21, the wing uses two flap sections, a root section closer to the fuselage and a tip section further outboard. When fully deployed for takeoff or landing, these sections sit in close proximity. Everything works as designed. But here's the problem. A problem that existed on every single flight, completely invisibly. During cruise, when the aircraft is flying at altitude with the flaps retracted, a gap opens up between those two sections. Just a gap. Air and space between two pieces of wing structure. So what? In aerodynamics, there is no such thing as just a gap. Here's what actually happens. The underside of a wing during cruise has higher air pressure than the top surface. That pressure differential is literally what generates lift. It's the fundamental mechanism that keeps 80 tons of aircraft airborne. But where there's a pressure differential and a physical gap, air will always find a way through. High-pressure air from below the wing leaks upward through the gap to the low-pressure region above. That leaking airflow disrupts the smooth, carefully designed flow over the upper wing surface. Lift decreases slightly but measurably. Drag increases. The aircraft burns more fuel to maintain the same speed and altitude. On any single flight, the effect is small. Multiply it across thousands of flights, across a fleet of dozens of aircraft, across years of operations, and you're looking at a significant compounding efficiency penalty. So how did the earlier versions of the MC-21 handle this? With imported elastic rubber seals placed at the flap tips. The concept was straightforward. During cruise, the seals would compress and bridge the gap, blocking the leakage path and restoring clean aerodynamics. Simple, logical, and in real-world testing, it didn't work. Here's the thing about aerodynamic pressure at cruise conditions. It's not gentle. At cruising altitude, air is moving over and under that wing at hundreds of kilometers per hour. The forces involved are substantial and constant. When those aerodynamic loads were applied to the rubber seals in actual flight conditions, the seals didn't compress cleanly as designed. They deformed, unpredictably, asymmetrically, in ways that the controlled laboratory testing hadn't revealed. And deformed rubber in an airstream doesn't just fail to seal the gap. It actively makes things worse, creating irregular surface geometry that introduces new turbulence, new drag, and in some cases more aerodynamic disruption than the original gap it was meant to close. This is the kind of problem that haunts aircraft programs. Not catastrophic, not dangerous, but persistent, stubborn, and resistant to easy fixes. The imported solution had a fundamental weakness that only showed up under real operating conditions. And when the supply of those imported seals was cut off, engineers faced a choice: find another imported substitute with the same underlying flaw, or actually solve the problem properly. They chose to solve it. The solution they developed is elegant in the way the best engineering solutions always are. It seems almost obvious once you understand it, which means it took genuinely creative thinking to arrive at. Instead of trying to passively fill the gap with a material that deforms under pressure, engineers designed a movable flap end mechanism. A small structural element at the tip of the flap that actively manages the gap geometry. During cruise flight, this element automatically extends to fill the gap between the two flap sections. The leakage path closes. Airflow over the upper wing surface stays clean. Lift is maintained. Drag is minimized. When the flaps deploy for takeoff or landing, the mechanism retracts automatically, clearing the way for the flaps to function exactly as designed without interference. But here's the detail that elevates this from a good solution to a genuinely impressive one. No additional actuators. No additional power systems. No extra electrical connections. No new hydraulic lines. The mechanism works entirely through the natural geometry of the existing flap structure. As the flaps move through their normal range of motion, the mechanism moves with them, driven by the same physical relationships that already govern flap deployment. Think carefully about what that means. In aviation engineering, every additional system is a potential failure mode. Every added component is added weight. Every additional power draw is reduced efficiency. And every new mechanical system requires its own certification, its own maintenance procedures, its own spare parts inventory. A solution that solves the aerodynamic problem and simultaneously eliminates the complexity and weight penalty of the previous approach. That's not just an improvement. That's the kind of engineering insight that defines a program's maturity. Better aerodynamics, maintained lift, reduced drag, zero additional complexity. The redesigned flap system is currently being tested on a fully import-substituted MC-21-310 aircraft. Production is underway at the Kazan manufacturing facility, a city that has quietly become one of the most important addresses in Russian aviation. But the flap story, impressive as it is is actually just the entry point to a much deeper transformation happening across this aircraft. Because the bigger story, the one with the most long-term significance, is what's happening with composite materials. Let's talk about composites, because this is one of those topics where the word gets thrown around constantly, but the underlying reality rarely gets explained properly. At the most fundamental level, composite materials, primarily carbon fiber reinforced polymers, combine two properties that almost never coexist in conventional materials: extraordinary strength and extraordinarily low weight. Steel is strong but heavy. Aluminum is lighter but less strong. Carbon fiber composites are stronger than both and lighter than both. In an industry where every kilogram of structural weight carries a direct, lifelong fuel cost, that combination isn't just attractive. It's transformative. A lighter aircraft burns less fuel on every single flight. Over a 25-year service life, the fuel savings from aggressive composite use can amount to hundreds of millions of dollars for an airline operating a large fleet. That's not a marginal advantage, that's a program-defining competitive factor. Composites also resist fatigue and corrosion in ways that metals don't. Aluminium structures develop fatigue cracks that require regular inspection and occasional repair. Carbon fiber structures are far more resistant to cyclic loading, which translates directly to reduced maintenance costs and extended service intervals. This is why Boeing used composites for 50 of the 787 by weight. Why Airbus did the same with the A350. Why every major narrow-body program is pushing composite content higher with each new generation. The MC-21 was already notable, aggressively so, for its composite wing. One of the most composite-intensive wing designs on any narrow-body aircraft in the world. That wing is a genuine technological achievement, and it was central to the MC-21's performance claims from the very beginning. But originally, that wing relied on foreign composite materials and foreign manufacturing expertise. When that supply was cut, the question facing the program wasn't just logistical. It was existential. Can you replace not just the materials but the entire manufacturing knowledge base with domestic alternatives? Under sanctions? Under time pressure? Without compromising the structural performance that the aircraft's entire efficiency case was built on? The honest answer at the time was, we don't know. The scope of what needed to be achieved went well beyond the wing. The tail assembly, the vertical stabilizer that controls yaw, the horizontal stabilizer that governs pitch, and the internal structural components that tie it all together, these also needed to transition to domestically produced composites. And these aren't minor structures. The tail assembly is fundamental to flight control and stability. An aircraft with a compromised tail structure isn't inefficient, it's dangerous. The material and manufacturing standards here are among the most stringent in the entire airframe. At the Kazan facility, engineers implemented autoclave-based manufacturing to produce these components. An autoclave, in industrial composite production, is essentially a large pressure vessel, a controlled environment where heat and pressure are applied simultaneously to cure the composite material. The autoclave eliminates voids in the material, consolidates the fiber layers, and produces the uniform, predictable structural properties that aircraft certification requires. Getting autoclave manufacturing right for large, complex primary structures is genuinely hard. It requires precise process control, temperature uniformity across the entire component, pressure management throughout the cure cycle, careful handling of material that's sensitive to time and temperature before curing. Small deviations produce structural nonconformances. And in aircraft structures, nonconformances require either repair or rejection. Building this capability from scratch in Russia under sanctions, that was not a given. But here's where the story takes its most unexpected turn. The domestic prepreg materials, the pre-impregnated carbon fiber sheets that form the foundation of composite structures, weren't simply reverse-engineered from foreign specifications. Engineers tested multiple material formulations. They characterized different fiber types, different resin systems, different processing parameters. They built an empirical understanding of what worked and what didn't, specific to Russian raw materials and Russian manufacturing conditions. And the material they ultimately selected didn't just meet the mechanical performance of the imported alternatives. In several key properties, it exceeded them. But something even more significant emerged from this process. The new domestic material enabled manufacturing techniques that the imported material couldn't support. Process paths that simplified production. Cure cycles that were more forgiving. Component geometries that were difficult or impossible with the previous material system. Let that sink in for a moment. The forced redesign didn't just replace a foreign material with a domestic equivalent. It produced a material that opens manufacturing possibilities the original never could. Components are being produced at lower cost. Workflows are simpler. Logistics costs have dropped because supply chains are fully domestic. And the quality, validated through rigorous testing that certification demands, meets international standards. Sanctions were supposed to make the MC-21 worse. In this specific domain, they may have made it better. That's not spin. That's documented engineering outcome. None of this happens without the right manufacturing infrastructure. And the story of what's been built at Kazan is one of the less told but more important chapters of the MC-21 program. Kazan has emerged as the hub of Russia's composite manufacturing transformation for this aircraft. The facility there isn't just producing components, it's functioning as a development center, where engineers refine production methods, characterize new materials, and adapt processes for new design requirements as they evolve. Why does manufacturing infrastructure matter as much as the engineering itself? Because you can design the most advanced composite structure in the world, and if you can't manufacture it consistently, if the quality varies batch to batch, if the process is sensitive to operator skill, if production rates are limited by manual process bottlenecks, then the design advantage never fully materializes in the real world. Manufacturing is where engineering ambition either gets realized or diluted. And this is exactly why the next phase of development at Kazan is so significant. Automation. Engineers are actively integrating robotic systems into composite manufacturing processes. Automated material placement, where robotic systems lay up carbon fiber layers with sub-millimeter precision, at consistent speeds, with zero variation between components. Precision-controlled cure cycles that maintain exact process parameters throughout production, shift after shift, component after component. What does automation actually change? Everything ultimately. Consistency first. Human composite layup is skilled work, genuinely skilled, requiring trained technicians who develop judgment through years of experience. But human hands introduce variability. Fatigue affects placement precision at the end of a long shift. Different technicians have subtly different techniques. These variations are small, but they accumulate, and in primary aircraft structures, accumulated variation means tighter quality control margins, more inspection time, and more rework. Robotic systems don't get tired. They don't have off days. Every component they produce is effectively identical to the one before it. That consistency simplifies certification, reduces inspection burden, and improves structural predictability across the entire fleet. Speed second. Automated systems can run continuously at rates that manual processes simply cannot match. And the materials being developed for the MC-21 are being specifically formulated to work with automated processes. Another example of the program's materials and manufacturing technologies co-evolving rather than developing in isolation. This matters enormously for the program's long-term ambitions. Russia has targeted a steady-state production rate of 2 MC-21 aircraft per month. Reaching that target requires manufacturing processes that can scale efficiently. Manual composite production cannot get there. Automated production can. The infrastructure being built in Kazan isn't just for the current program. It's the foundation of a domestic aerospace manufacturing capability that will outlast any single aircraft type. But even with all of this, the aerodynamics, the composites, the manufacturing, there's still a layer of the MC-21's transformation that most people haven't fully appreciated. More than 70 components have been localized on the MC-21-310. 70. Read that number again and think about what it actually represents. This isn't just an engine and a wing. The localization program covers avionics, the flight management computers, navigation systems, and display systems that pilots use to fly the aircraft. Auxiliary power units, the small turbine engines that provide ground power and air conditioning when the main engines are off. Environmental control systems, the complex pneumatic and thermal management systems that pressurize the cabin, regulate temperature, and maintain the oxygen levels that keep passengers and crew conscious at 12,000 meters altitude. Cockpit equipment, communication systems, redundant safety systems throughout. So what does it actually mean, practically, operationally, to have all of this localized? Let's think about it from an airline's perspective. When a foreign-supplied component fails on an aircraft, the airline contacts the foreign manufacturer. They request a replacement part. That part may be in stock, or it may need to be manufactured. It needs to clear export controls, which in the current geopolitical environment can be complicated, delayed, or simply refused. It needs to be shipped internationally, clear customs, and reach the maintenance facility. In the best case, this takes days. In difficult geopolitical circumstances, it can take weeks or become impossible. Every day that aircraft sits on the ground waiting for a part is a day it's not generating revenue. For a narrow-body aircraft in regular service, that's a significant daily cost. Now replace every one of those foreign components with a domestically produced equivalent. The supply chain compresses from international to domestic. Parts availability becomes a logistics question, not a geopolitical one. Lead times shrink dramatically, and the airline's dispatch reliability, the percentage of flights that depart on schedule, improves in direct proportion. In commercial aviation, dispatch reliability is one of the metrics that airlines live and die by. It affects passenger satisfaction, schedule integrity, and ultimately, an airline's competitive position. An aircraft with a robust domestic supply chain has a structural operational advantage that never appears in a spec sheet, but shows up every single day in the maintenance logs. But here's the real complexity that deserves acknowledgement. Localizing 70-plus components isn't 70 separate engineering tasks that can be parallelized and completed independently. Each system interacts with others. Avionics must integrate with flight control systems. Environmental controls must interface with structural monitoring systems. Changes to one system propagate requirements through others. The systems integration challenge, making all of these independently redesigned domestic systems work together seamlessly, safely, and in certified compliance with international airworthiness standards, is one of the most demanding aspects of the entire program. And it's exactly what the MC-21-310 is currently working through in certification testing. Multiple aircraft are flying extensive test programs right now, accumulating data, identifying integration issues, validating performance, and building the body of evidence that regulators require before a type certificate can be issued. Every flight hour is progress. But the finish line still requires everything to work together, not just individually but as a unified, integrated system. Step all the way back now, because there's a conversation happening around the MC-21 that I think deserves to be had directly. When sanctions were imposed and the MC-21's foreign supply chains collapsed, the conventional wisdom was straightforward: Russia's aviation ambitions would be significantly set back. The program would survive in diminished form, producing a domestically configured aircraft that was meaningfully inferior to the original foreign-equipped version. A political statement, not a technical achievement. That assessment is proving to be wrong. At least in part. Not wrong in acknowledging the difficulty. The program has been harder, more expensive, and slower than planned. That's real. Not wrong in noting that Russia still faces significant gaps in certain aviation technologies. Those gaps also exist. But wrong in assuming that forced domestic development would produce only inferior results. The flap mechanism is better than what it replaced. The composite materials are enabling new manufacturing capabilities. The production infrastructure being built in Kazan is genuinely world-class in its domain. And the question this raises is one that has implications well beyond Russian aviation. What does it take to build real, resilient, independent technological capability in a critical industrial sector? The MC-21 experience suggests the answer is painful, expensive, and time-consuming, but ultimately achievable. And it suggests something important about the relationship between constraint and innovation. That being forced to solve a problem from first principles, without the option of buying your way out of it, sometimes produces better answers than the comfortable incremental approach ever would. Is Russia's aviation industry fully independent now? No. Are there still critical gaps? Absolutely. But the trajectory is clear. And the specific achievements of 2026, the patented flap design, the domestic composite breakthroughs, the 70-plus localized components, these aren't narrative. They're engineering facts. Documented. Testable. Real. There's an idea in engineering, really in any domain where people try to build hard things under difficult conditions, that constraints don't just limit what you can do. Sometimes they reveal what you must do. When the easy path closes, you find out what the problem actually requires. Not what was available. Not what was convenient. What the physics, the aerodynamics, the structural mechanics actually demand, if you're willing to start from zero and think clearly. The MC-21 in 2026 is the product of that kind of thinking. The flap mechanism that solves a real aerodynamic problem more elegantly than the imported rubber seal it replaced, and does so with less mechanical complexity, not more. The composite materials that don't just match foreign predecessors but enable manufacturing processes the originals couldn't support. The 70-plus localized systems that together create an operational independence no supply chain disruption can threaten. The automation pipeline being built at Kazan that will enable production rates manual manufacturing could never reach. None of this was inevitable. None of it was guaranteed. It required engineers willing to question assumptions they'd inherited from foreign designs. It required manufacturing facilities willing to invest in genuinely new capabilities under genuinely difficult conditions. And it required program leadership with the discipline to pursue better solutions rather than just faster ones. The MC-21 is not a finished story. Certification testing continues. Production scaling is ongoing. The path to full commercial service still has real distance to cover. But the question has changed. It's no longer can Russia build a competitive aircraft independently? The question now is what does this aircraft become once it's in service? And beyond that, what does it mean for a world increasingly defined by technological competition and supply chain fragmentation, when a program forced into self-reliance emerges not weakened, but in several measurable ways stronger? That's a question worth thinking about carefully. And I'd genuinely like to know where you stand. Drop your thoughts in the comments. Do you think the MC-21 can compete beyond Russia's borders? Or does domestic capability ultimately need global validation to mean anything? If this level of analysis is what you want more of, subscribe, share this with someone who takes aviation seriously, and hit the like button. It genuinely helps this kind of coverage reach people who care about it. See you in the next one.